All right, so this is simple harmonic motion. All right, so now let me show you another app. Okay, so this is the phenomenon we're going to study. Okay, we're going to study what you see is a wave traveling on this string. Now the question is there any relationship to that simple harmonic motion?
Yes.
And what is the relationship?
The peaks in the valleys of the string keep going up and down like the string goes up and down.
Every point in this medium is executing simple harmonic motion. Okay? So again, in education, this is the deal. We'll first introduce you to a brick, and then we'll use 1,000,000 bricks to build a house. Okay? So here are all these simple harmonic oscillators in choreographed motion. Okay? So this is what we're going to study. Okay? Now, you saw the first introduction to differential equations last chapter. Okay. What were differential equations used for? They were used to model the behavior of systems like that. Okay. So we will introduce the wave equation. We'll introduce a differential equation that describes the behavior of the system. Okay. All right, so that's the goal. We'll talk about waves. Why do we talk about waves? Your,
Everything is a wave.
your life depends on waves. I'm talking that energy was transmitted by a sound wave to you. All communication happens through waves. You guys can't live without this thing.
I could.
Huh?
I could.
Okay. Yeah. Well, you're very uniquely good. Okay. So, um, so anyway, our lives depend on waves. Okay. So we're going to talk about properties of waves. Okay. So each particle is executing simple harmonic motion. Okay. All right. So that's the progression. Okay. So we'll talk about waves. Initially, we'll go through some terminology and simple terminology that you'll understand. Okay, so we'll talk about different kinds of waves: mechanical waves, electromagnetic waves, matter waves. Mechanical waves are waves that need a medium to travel through. Electromagnetic waves can travel through perfect vacuum. Okay. Can you give me an example of that?
Would sound be a mechanical wave?
Sound wave is a mechanical wave, but an example of an electromagnetic wave.
Light?
So sunlight is coming to you from the sun to here through 100 million miles of perfect vacuum. Okay? Then we'll talk about matter waves. Well, we won't talk about matter waves, but okay, you guys want me to show you this YouTube video, which is a 4 or 5 minute video? You guys want to see that?
Sure.
Okay. All right, so let's see that. See, it doesn't mess up here. Okay, what is this connected to AirPlay? All right, you guys go see that video. I don't know, when I do screen recording, it doesn't seem to show the video. Okay. All right, so matter waves, here's the deal. Okay. And this is what the video will show you. Okay, so you will learn as you, so here's an electromagnetic wave. Okay. And by the way, so this is crest to crest distance. This is called wavelength, denoted by lambda. Okay. And different wavelengths have different colors to them. Okay. You perceive them as different colors. Okay. So let's say you have a wave traveling like that and it reaches this point, and now I'll use a different color, but the same wavelength. Okay. So let's say this wave travels like this. What do you think will happen here? They'll cancel each other out. So very good. So only if only this wave had come, you would see light here. If only this wave had come, you would see light here. If both of these waves reached here, you would have a dark spot there. Okay? So I'm telling you what you'll see in that video. It's mind-boggling. Yeah. You guys understand this? This is called constructive and destructive interference. Okay, so now we'll do the following experiment. We'll take a screen which has double slits. Okay? We'll shine light on it. So this is light. Okay? One wave travels there and reaches this wave. One wave travels here and reaches here. And here you have constructive interference, meaning two crests are meeting. Here you have destructive interference, meaning a crest is meeting a trough. Here, a crest is meeting a crest. Did you guys understand that? Okay, so this is the double slit experiment that you'll see that light exhibits. Okay, so you'll see a series of bright fringes, dark fringes, bright fringe, dark fringe, bright fringe, and so on. Okay. All right. Now I'm going to do the same thing, except that I'm going to get an electron gun. Okay? I'm going to shoot one electron at a time, like a BB gun. You've been to college. What do you think will happen? I mean, if you're smart, you would say that a whole bunch of electrons would hit here. You'd see a spray of electrons here, a whole bunch of electrons hitting here, and you'll see a spray of electrons.
You're gonna get what looks like waves if you're gonna get particles if you observe it, and waves if you don't observe it, or one way or the other?
So I'm asking you first, let's bite the steak one bite at a time. Eat the steak one bite at a time. So I shoot the electrons. What do you expect? patch of, right? A bunch of electrons there and a bunch of electrons there. That would be the most natural thing to say.
Radio waves.
So you do this experiment, and we took a lot of trouble to do this experiment. Okay? So we're going to shoot one electron at a time, and you get exactly the same pattern as the light. So what this experiment proves is this particle that you're so used to thinking as like a bullet or something like that is behaving, it has wave-like properties. And these are called matter waves. Okay. And the wavelength of this matter wave is given by h, the Planck's constant, divided by the momentum, which is mass times velocity. Okay, so the faster the particle is moving, the smaller the wavelength. Okay? Or more massive the particle, smaller the wavelength. That's why it's very hard to notice your wavelength, but you do have wave-like properties, except that your wavelength is so small. Okay, so if you want to detect a wavelength that small, you need an object that small. The size of the wavelength, you need an object that small. Okay? So if the wavelength is too small, much smaller than the size of an atom, there's no way you're going to detect it. Okay? Much, much smaller. So that's what that is. So I urge you guys to go see the video. Okay? And the more you think about it, the more crazy you'll be. Okay? You'll get. Okay? So go watch that video. All right, so we're going to talk about different kinds of waves. Mechanical waves are waves that need a medium to travel. Okay, so sound waves are mechanical waves that need a medium to travel. So out in space, where in perfect vacuum, you cannot have sound waves. Okay? Electromagnetic waves can travel through perfect vacuum. They're waves made of electric and magnetic fields, which we'll talk about next semester. And matter waves are waves associated with matter particles. Okay? So those are totally different kinds of waves. Okay. We'll come to this picture in a second. Okay. So when a wave travels through a medium, matter is not transported. Okay, so let's illustrate that. So you can see that in this, the wave is traveling to the right, but those particles of the medium themselves are not traveling. Okay? So it's a disturbance that is traveling. And you guys experience this in stadiums when a wave goes through the stadium. The spectators are not traveling. Okay? You can put a piece of wood in water, and a wave will travel through the water, but the piece of wood will just bob up and down. Okay? So the medium doesn't travel. Okay, it's a disturbance that travels. And this wave carries energy. How do you know it carries energy? Can you give me?
Because the particles are oscillating, which is...
So, yep, so very good. So let's say you anchor a boat there, you drop a rock here, and the wave will propagate, and what will happen to the boat? It'll bob up and down, and you need energy for that. You can go stand outside in the sunshine. An electromagnetic wave came from the sun. When you absorbed it, you felt warm. Okay, so waves carry energy. All right, so waves, when a wave travels through a medium, matter is not transported, only the disturbance travel, and all waves carry energy. Okay. Again, we're just introducing terms. Okay. So the crest to crest distance is the wavelength. So these are some properties of the wave. Amplitude, the amplitude is the maximum displacement. So if this is the undisturbed position, this is the amplitude. Okay, and amplitude is the intensity energy being transported per second per unit area is related to amplitude. When I talk louder, the amplitude increased. Okay, So if you have a more intense beam, then the amplitude of the stuff is greater. So here's a very bright laser. So the amplitude of the electric field is larger. Okay. All right, so amplitude is related to the intensity of the wave. Yeah. All right, we'll talk about longitudinal waves. Oops, what happened to transverse? Okay, so transverse waves and longitudinal waves. Okay. In transverse waves, here's the deal. If the wave is traveling in this, so if this wave travels in that direction, the particles of the medium are oscillating perpendicular to the direction of travel. Those are transverse waves. Okay. And so you see this is a transverse wave. The wave is traveling in this direction, the wave is traveling in this direction, and the particles are oscillating like that. Okay. In a longitudinal wave, the wave travels this way, and the particles also oscillate in a direction parallel to the direction of travel. Okay. So in a transverse wave, the wave travels in that direction and the particles oscillate like that. And in the longitudinal waves, the wave travels that way and the particles oscillate parallel to that. Yep. And let me show you a simulation for that. Okay, so here is a simulation for a sound wave to make, this is a sound wave propagating in a gas, so air for instance. You can generate a sound wave, all you need is a diaphragm and make the diaphragm oscillate. Okay, remember a wave is carrying energy away, so if you don't want the wave to die, you have to keep pumping energy in. Okay, so here, I'm creating a sound wave. What happened? I'm not creating a sound wave anymore. Here's a sound wave. How come you're not hearing it?
You aren't very fast.
What's that?
You aren't very fast.
That's right. His sensor is not designed for this. Okay. His sensor is designed in a very narrow window, 20 hertz to 20,000 hertz. There are systems that could detect this. An elephant probably can. Okay. All right, so so you see the wave is traveling in that direction, and if you look at each particle, they're oscillating in a direction parallel to the direction of travel. Yeah, those are longitudinal waves. In a transverse wave, the wave travels that way, and the particles oscillate perpendicular to this. Water waves that we all experience, those are complex waves. In a water wave, each particle is going in a circle. So it's a combination of a transverse wave and a longitudinal wave. Okay. So if you have a 3-foot wave, the water molecule is going in a circle of radius 3 foot. Okay. And as you go deeper, the size of the circle gets smaller and smaller. All right, so those are just terms. So complex waves are a combination of longitudinal and transverse waves. Okay. So what is wavelength? Wavelength is crest to crest distance. Okay. And in light, for the colors, for the wavelengths that your sensor works, okay, different wavelengths correspond to different shades. Okay. You guys, your eyes are sensitive to about 7 million shades. Okay. So, and your sensors are sensitive to nanometers, okay, 400 to 700 nanometers, okay. So in that range, you can perceive 7 million different shades, okay. Now here's one fact I want you to remember forever. how do you sense something? How do you see something? Yeah?
With the cones and rods in your eye.
Yeah. Okay, so we'll go, yeah, very good. Okay, the way you see something is you send a probe, the probe reflects off the object, and then you have a sensor to sense that. Okay? So this is the object you want to see. You send a probe is some kind of a wave, and then the wave reflects off, and then you sense it. Okay, so here's a very important fact. If you want to see this object, okay, you can't see this object with a probe of that wavelength. Did you guys understand that? So to see an object that small, you have to have a wavelength smaller than the object or the size of the object. Okay? Did you guys understand that? So if you wanted to see a tennis ball, a radio wave will have a wavelength like that, and you couldn't see a tennis ball with a radio wave. Okay? So remember that. Okay, so with this wavelength, you can see any object this size or larger. Okay? All right, so this will be useful. So for instance, if you wanted to see an atom that big, what do you need? You need a probe whose wavelength is smaller than the atom, and those are X-rays. Okay, you can't see atoms with visible light. Visible light have wavelengths like that. Okay? All right, see, visible light has wavelengths of 500 nanometers. And the size of an atom is 1/10 of a nanometer. So visible light has wavelength of 5,000 times the size of the atom. There's no way you're seeing an atom with a visible light. Okay? All right. Again, I just want you guys to think about stuff. Okay, you guys can read the slides later. Yeah. The period, what do you think is that?
The time it takes to get from crest to crest.
Yeah, so as this wave travels, this, whatever it is that's oscillating, oscillates like that. The time for one oscillation is the period. And here's another way to think of the period. Okay, so here's a wave. So you all are familiar with water waves. You can stand here and count the time it takes for one wave to pass you. That's also the period. Okay, the time for one oscillation and the time for one wave to pass you by. Okay. Frequency is the number of oscillations per second, and that also happens to be, if you're standing there, the number of waves that will pass you in 1 second. Okay? Okay. Frequency and period are inversely related. Okay, one of our goals is to mathematically model the behavior of this system. Do you guys remember what kind of equation you'll get? What will be the mathematical model?
Similar to a spring.
Yeah, so it'll be a differential equation, okay? And we'll talk about partial differential equations. All right, so we are interested in, we are sophisticated people. We want to mathematically describe everything. Why do you want to mathematically model something?
So you can predict its behavior.
Yeah, you can study this in lab. You'll get your hands dirty, and it'll take you months and months to study the system. You have a mathematical model, spend $300 in the math department, and in 30 seconds, they'll teach you how to analyze this stuff. Okay? So you can analyze things much faster. You can learn about systems much faster. Okay? And we want to know the true nature of things. So mathematical model is the fastest way to get there. Studying stuff mathematically is the best way to get there. All right, so to get there, we'll need to define some terms. We'll define the wave number, denoted by K, and that's 2 pi divided by lambda. Okay. So you can think of it as, in this length, how many wavelengths can you fit? Smaller the wavelength, larger the wave number. Okay? We'll define something called angular frequency denoted by omega. It's 2 pi times f, angular frequency. So if this is the linear frequency, f is the linear frequency, and omega is the angular frequency. All right, so now we're going to build the mathematical model. Okay, so here's a very, I love this trick. You guys have all learned this in your calculus classes. So let's say here's a function. Okay, so this is f of x. And what I'm interested in doing is I want to transport this to the right. Okay, so here's what I want to do. I want to transport this by c.
F of x plus c.
I'm sorry?
F of x plus c.
F of x minus c. Okay? So if you want to transport it to the right, it's f of x minus c. You guys remember? You want to transport it to the left, it's f of x plus c. All right. Think before you shoot. Okay. Now I'm going to want to do the next complex thing. I'm just not interested in just transporting this like that. I want it to travel at velocity v. Think before you. How do I do that? All right, so I'll give you a hint so you can build it. In 1 second, how far will it be? How far will it have traveled?
V meters per second.
V meters. Okay. In 2 seconds, how far will it travel?
2 V meters.
2 V meters. So in t seconds, it'll travel that distance. You already know how to transport it to the right. So here's a pulse traveling to the right at velocity v. Here's a pulse traveling to the left at velocity v. You guys understand that? All right. So see, in 30 seconds, you're already learning this. So now let's do this. Okay. So, oops. This is y equal to a is the amplitude. There's the lambda, k is 2 pi by lambda. Okay, so what I'm saying is this function is that, sine kx. Okay, let's make sure of that. For x equal to 0, what is sine 0? 0. Okay? For x equal to lambda, kx will be, what will be kx? 2 pi by lambda
Just 2.
times lambda, it'll be 2 pi, sine 2 pi is 0. Okay? So, who's that? Okay. What's that?
We stole their room.
Well, they have it at 3 o'clock. Yeah. And I have higher priority than that. All right. So this is given. This function is given by sine a sine kx. All right. Now let me ask you this. I want you to move this to the right at velocity v. You should be able to do that.
A sine k of x minus v of t.
There you go. What is this? A sine k x minus vt. What is that? You just described that guy. This traveling wave, you described that. Okay? So you have a solution to some equation that models the behavior of that. Okay? And now we'll introduce that differential equation to you. Did you guys understand that? So what would k of x plus vt be?
I think to the left. of
Where you're traveling to the left. All right? All right. So that's what we're building towards, okay? All right, so you understood all of that. Here's a pulse traveling to the right, and so here's, okay, so now let me make sure we understand this portion. I'm going to show that this is a wave traveling to the right, okay? Um, so as our friend just said, this is a wave traveling to the right, so y x t, now it's a function of x and t, a sine k x minus vt. Okay, in a second you will learn that the velocity of the wave is given in terms of frequency and wavelength like that. Okay, so I'm jumping ahead a little, but sine, so this is sine k x minus v is frequency times lambda times kt. Okay. And k is, so f lambda times 2 pi by lambda t. The lambda cancels, and it's 2 pi f t. Do you recognize this? What is 2 pi f?
2 pi f is
Omega t.
angular frequency.
Omega, angular frequency, so omega t. All right, so here's a different way of writing it, a sine wave traveling to the right. Okay, this is written in terms of the wave number and the angular frequency. Okay, so this is very useful because you encounter this all the time. Okay? So here's a sine wave traveling to the right, and here is a sine wave traveling to the left. Okay. Now, why would we talk about this kind of stuff? Because when you pluck a guitar string, you'll have a wave travel to the right. It gets reflected at the fret and then comes back. Okay, so in a guitar string, in most musical instruments, you'll have identical waves traveling to the right and left. Okay, and when you have identical waves traveling in a given medium in opposite directions, what they do is they create a standing wave, and we'll come to that in a second. Okay. All right, so so here's a wave traveling to the right. And so what this tells you is, okay, now I'll just show you the picture. So here is that wave that is traveling to the right. What does this point correspond to? If you think of the sine wave, this is the maximum. So this point corresponds to the phase being pi by 2, 90 degrees. This guy is called the phase. Okay, so that phase is pi by 2. Okay, and what is this phase? That's also pi by 2. So what is happening is, as t increases, for this to be pi by 2, as t increases, what you have to do, you have to move further right to get this value to be pi by 2. Did you guys understand that? Okay, so the speed at which the constant phase points move to the right is the velocity of the wave. Okay, and so that's so this is constant, and you take the time derivative of that, and so the velocity of the wave is frequency times the wavelength. Okay, all right. Now this formula is true for all waves. Okay, so we're talking about general properties of these waves. So you guys are already experts now. This is a sine wave traveling to the left. Okay. This is the wave number. This is the angular frequency, the velocity of the wave. So you just saw a minute ago the velocity of the wave is that. and that is also equal to, in terms of the angular frequency in that, it's also given by that. Okay? All right, so remember that. All right, I'll be back in a second. Yeah, I'll be done at 2:30.
Oh, yeah, no problem.
Okay, you wanted at 3 o'clock, right? The room?
2 to 3.
Oh, you want?
Sorry, I was wrong on the time.
Okay.
It's 2 to 3.
Can you mind going to the next room?
Yeah, I'll find a room.
Okay, thank you so much. All right, so here's a wave traveling on the string, okay? Now watch this. What I'll do is, okay, you guys have all used ropes and you've sent waves down a rope, okay? If the rope is slack, if the tension is low, what happened? The wave travels slower, okay? I'll increase the tension and the wave will okay, so the speed of the wave increases. So for instance, you can't send a wave down a cooked spaghetti, okay? You can't put tension there, and so you can't send a wave down, okay? And let's, you can't make it heavier, okay? So that's what this formula tells you, okay? The velocity of a wave on a string depends on the tension in the string and the mass per unit length of the string. Okay, so the heavier the string, lower the velocity. So you've experienced this in a guitar. The thicker string has greater mass, and so the velocity is lower, and velocity is frequency times wavelength. Wavelength depends on the length of the string. So all strings are of the same length. So heavier the string, lower the frequency. Okay, it produces bass sounds. Okay. You guys understand that? Okay. All right, as a wave travels, what is it carrying with it?
Energy.
Energy. Okay. So what we want to do is we're going to stand here and we want to ask the question, how much energy is passing us each second? Okay. Why do we want to know that? Well, I mean, that's money going out of your pocket. The more energy you send down, the more money it's costing you. Okay. So if you want to communicate further, you have to send a brighter signal because it spreads out and stuff like that. As radio station in Orlando, if it wants you to catch the signal here, it has to send a stronger signal. If it wants to broadcast only to Orlando, then it doesn't have to send as strong a signal. Okay? Why would you want to reach here from Orlando? Why spend more money?
To send a message.
And now your advertising area increases. Okay, you can increase your advertising revenue. Okay? So, all right, so here's the rate of energy transmission. So what we're going to do is we're going to send a wave down a string. We're going to stand here and ask how much energy passes you by per second. Okay? And here's the expression. The average energy passing you per second is 1/2. Mu is the mass per unit length of the string. Heavier the string, more the energy is going. V is the velocity of the wave. Omega is the frequency of the wave, angular frequency of the wave. Yes? Faster it's oscillating, more energy is passing you. And A is the amplitude. Remember, if I talk louder, I'm projecting more energy. Okay? And you can hear me further up. Yeah. So anyway, so that's the expression. So here, this is, you have to remember, well, you will encounter this future in whatever you do. the power emitted depends on the frequency square and the amplitude square. Okay. Okay. So I told you we're going to model the behavior of this system, and the mathematical model will be a differential equation. We're not going to derive it, we'll just give it to you because you guys are nice. Okay. So what is happening here? Let's look at this. Okay. So here's the y coordinate of this of the string. If you and there's the x coordinate. If you stand at a particular point, what happened? All right, so if you stand at a particular point, the y coordinate is changing with time. Okay, and now let me freeze it. And if you travel down the x coordinate, the y coordinate is changing. Okay? But you already knew that. See, you wrote that traveling wave here. You wrote that. So y equal to x is a function of x and t. Okay? So when you wrote that traveling wave, so I'll write a cleaner version. As this wave travels down with the velocity v, y was a function of x and t, a sine kx minus omega t. Okay, now I forget, so remind me please, what is a? Amplitude. What is k? What is it related to? To the wavelength. So it's the wave number. What is omega?
The 2 times
Angular frequency. So it's related to the frequency. Okay, so you know all those terms. This is the wave traveling to the right. All right, so it turns out that, and again, I'm not going to derive this. The behavior, this is a very complicated looking behavior. Okay. So the y coordinate, so the y position, the location of that string, I don't know why it does that. Why does it do that? Is given by this differential equation. This is a partial differential equation. Okay, remember y was a function of x and t. Okay, let's look at this equation closely. Okay, this is sort of a strange equation. This is partial derivative with respect to x, the second partial derivative with respect to x. What does partial derivative mean?
derivative with just respect to y or derivative with just respect to x.
Oh,
So you treat the other variable as a constant.
that's right. Okay, you guys remember that? So let me give you an example. So y, I'm just, this is a simple example. X squared t cubed del y by del x would be 3 or 2x t cubed del y by del t would be x squared 3t squared. Okay? So when you're taking derivative with respect to one variable, you're keeping all the other variables constant. That's what partial derivative means. Okay? So if you're going in the x direction, how does y change when you're going in the x direction? And how does y change when you're going in the t direction? Okay? If you want to think of it that way. All right, now let's look at this equation. So what the equation is telling you is how y is changing as you travel down in the x direction. Okay, that's the second derivative in the x direction. And that's related to how y is changing at a given location with time. Why the heck should they be related? Did you guys understand that?
From
This,
the formula we derived,
what's that?
since, because y is dependent on both x and t.
Right, so it turns out that the change of this wave in the x direction is related to how it's changing at a given location with time. Okay? So this is the partial differential equation. Okay, so it's relating the second order spatial derivative to the second order time derivative. Okay, now here's another thing I want you to remember. So here's y, y is a distance. You have x squared in the bottom. Okay, that's x squared in the bottoms, and v times t is distance, so v squared times t squared is distance squared. So it has the right dimensions. Remember, if you have apples on the left-hand side, you have to have apples on the right-hand side. So this has to be a velocity. Okay, so here's this system. Here's the partial differential equation that models the behavior of that system when as waves are traveling down this. Yep.
Since it, is the reason you hear like a sonic boom when something's traveling at the speed of sound because y is dependent on both the position and time? So like they cancel out when it's moving at the same speed that the wave is traveling from, that the sound waves are traveling from an object?
All right, you asked too many things. So you start with the sonic boom. Just ask about the sonic boom. What is a sonic?
Is the reason you hear it because y is dependent on both x and t?
Oh, no. Okay. We'll come to sonic boom. Next chapter.
Okay.
Next chapter. Okay. All right, so this is the wave equation. And solutions to this wave equation, again, you'll learn how to solve these in differential equation classes, okay? And has this general form, x plus or minus vt, okay? And you already have a solution. The simplest solution was you sent a pure tone down the string. This is the simplest solution, okay? So plus or minus, yeah. Everybody understand that? Okay, you can send down a more complex wave, but this more complex wave will be a combination of these simple solutions. Yep. All right. So again, you will encounter this fellow a lot. Okay, so remember that. Again, very neat thing. It's relating the spatial derivative, how y is changing with space, to how y is changing at a given location with time. Yeah, very neat. All right, now we'll switch gears. Okay. What we have done is we've learned how to describe a single wave and stuff like that, and then now we're going to get two waves to interact, two waves or multiple waves to interact. Okay, we'll send multiple waves. So we'll all talk together and we'll ask him what does he hear. Okay. And you're getting light from all these sources. Okay. And what is the net effect at this point? Okay. So that's the kind of stuff we are interested in. Okay. So we'll use a string again because this is the simplest thing to illustrate. So we'll send down a pulse like that in this direction. So, and we'll send down a pulse like this in this direction. Okay. So here's a couple of things we'll notice. Okay. So when they reach the same location, they interact. Okay. And whatever happens, we'll say what happens in a second. And notice something else. What do you notice here? What is this telling you?
They just went their separate ways and were unaffected.
That's right. See, the interaction didn't change their shape. See, if I say something nasty to her, she'll go home and she'll be mad all day long. The waves don't care. Do you understand that? See? So, when they're at the same location, they just add. Okay? And that's constructive interference. Okay? So And you can do this for multiple waves. You can combine 1,000,000 waves together. You just add them together. Okay? And then once they've interacted and they go past each other, they'll go their separate way. Okay? All right. So constructive interference occurs when the amplitude of the resultant pulse is greater than either of the individual pulses. So see, the resultant pulse is bigger than either of those pulses. This is constructive interference. Okay? So the energies have added, and so let's okay. So going back to that double slit experiment, what happens here? You get a bright fringe, a dark fringe, bright fringe. Okay. So what happened? Energy just got redistributed. Here, this had 0 energy. Here, had twice the energy, and so on. That's all. Was energy created or destroyed? No, it just got redistributed with interference. Okay. All right. All right. So here they added, and again, so once they go past each other, they're not altered. Okay. This is destructive interference. If you have a positive pulse interfering with a negative pulse, if they reach at the same time, same location, you see at this location, this resultant pulse is smaller than the bigger pulse. So you have destructive interference. And if you have perfect destructive interference, you would have 0 there. Okay? And again, once they go past each other, they don't affect each other. Okay? All right. Now what we'll do is, what is this guy?
That is representing the wave.
What is this? No, just look at just that. That's a sine wave traveling to the right. That information has the wavelength, that has the frequency. What is this guy?
A sine wave traveling to the right with
What this does is, this is a phase shift. Okay, what that does is the following. So here's one wave, and here's the phase shifted wave. Okay, and so this is phi. Okay, that's the phase shift. Okay, so if this were 0, they're starting at the same location in identical manner. Okay, so here's a phase shift of 0. So 2 waves traveling to the right. Here's a phase shift of 180 degrees. So whenever you have a peak here, this has a trough. And so these waves are traveling to the right. Okay? Whatever location they reach, these 2 waves are always canceling each other. Okay? So I'll send these 2 waves with a phase shift of 180 degrees, and they reach this location and they're always canceling each other. You hear no sound. So how do you know that there were 2 waves canceling each other, or I was producing no sound? How do you know that? How can you tell the difference? Did you guys understand the question? Okay, so let's say I send 2 waves and she hears no sound. How does she know that 2 waves reached there and canceled each other, or no sound was being produced?
she doesn't know.
Is there any way she can find out?
By moving to a position where the waves don't cancel.
Exactly. So if she moves and at a new location, if the waves don't cancel, then there was sound being produced, and that happened to be a destructive interference spot. Okay, do you guys understand? All right, so this is 2 waves traveling to the right. If the phase shift is 0, this at any location, this would be, see, the amplitude of the wave is twice as much. If the phase shift is pi, they would cancel each other, and this is for another phase shift. Okay, this is the resultant wave. Okay. All right, now in musical instruments, it turns out that you have a wave traveling to the right and an identical wave traveling to the left. Okay, and that'll produce standing waves. Okay, so this is just showing you one special case. Okay. Now this stuff is hard to understand, but there will be times when you'll have to add multiple waves. So there's things called diffraction gratings, and I've shown these to you. So here is a wave coming from here, from every slit, okay? And you will need to combine many waves, okay? So you need a smart technique to add many waves, and that's what this is. So I'm going to spend, oh wow, 2 seconds on it. I'm going to finish it. Okay, I know it's 2:20, but I want to finish this lecture. Okay, so here's a vector A. What is the y component of the vector?
Hey, what?
In terms of A sine theta. Okay. Now let's say we make theta equal to omega t. What does that mean? As t increases, this angle is increasing. But that's the formula for ay is still the same. Ay is a sine omega t. All right, so this was the y coordinate for the string at x and t. Okay, so you can think of it, this is the amplitude of the wave, this is the amplitude of the vector, and there is the phase angle. Okay, so this is called a phasor. Okay, so here is the amplitude, and as t increases, the phasor is rotating to the right at angular speed omega. Okay, and the value at any given location is just the y component of that phasor. Okay. Now, so if you wanted to add two waves, then you would add this, and then you would have to use the addition formulas in trigonometry, and that if you have to add more than two, it gets to be a pain. And this technique helps you solve that. So if you want to add one wave, there's one phasor, just add the other phasor. There is the phase difference between the two. That phase difference was this phase difference. And the sum of those two waves is that. And that is rotating at that same angular speed. Okay? So using this technique, you can add millions of waves very easily. Okay? And that's what that technique is. Okay? I'm going to slightly speed up, but I want to finish this. Okay? So you will be interested in properties like this. Okay, you send a wave down like that, and this wave, when it hits the wall, it's reflected. And what happened?
It became upside down.
Like, so when it hits a hard wall, a positive pulse becomes a negative pulse. Okay? When it hits a soft wall, a positive pulse remains a positive pulse upon reflection. Okay? Well, why do we care about this? Okay, so here is why you care about this. Okay. Oh yeah, there you go. So here's what's happening. Okay. So you guys see this? What is that?
It's an oil spill.
So, okay, what happened was it had rained, there's water, and then some car leaked oil. So there's a thin oil film on water. Okay. So if you look at that portion, you're seeing that color. If you see that portion, you're seeing that color. What's happening is white light is falling on that oil slick, and depending on your angle, you're seeing different colors. So here's what's happening. Okay, so here is white light incident. Part of this light is reflected, part of it goes through the oil, gets reflected here, and goes through there. Okay, this reflection is like a hard reflection. Okay, when you hit a medium of refractive index greater than what you're traveling with, that's a hard reflection. It's like hitting a hard stuff. This is oil, and then you're hitting water. That's also a hard reflection. Okay, and again, so you need to know the phase shift. And here are these two reflected beams that are interfering. If you can see that color, that means that's constructively interfered. And if you can't see a color, those are destructively interfered. Okay. So nowadays you see these cars that as they pass by, you see different shades on the car. You guys know what I'm talking about? Okay, so how does that work? What they do is, nowadays they have these techniques where this is a clear plastic coating that they paint, except that you need to be able to coat a uniform thickness clear plastic coating. Okay, and all you're seeing is different colors being reflected. Okay, so that's what's happening. All right, so for thin film optics and all that, you need that. Okay, so now we'll talk about standing waves. That's what happens in musical instruments. So here's a wave. Okay, so for a wave to travel, what you need is x minus. Okay, you need a function of x minus vt, or x plus vt. Okay, for a wave to travel. So let's combine this. Here's a wave traveling to the right. Here's a wave traveling to the left. If you combine the two, here's the result you get. And you see, this is x and t are separated. It's no longer a function of x minus vt. It's a function of x and a function of t. Okay, and this is a standing wave. Okay, so here is the amplitude, and all that's doing is the amplitude is changing, but each point is oscillating at just like a mass attached to a spring. So this is a wave that's not traveling anywhere, neither to the right or left. And I want to show you this this simulation because it's important. I know you guys are getting restless, but I have to finish this and I have to show you this. Yep. So just be patient for 2 seconds. Where the heck are standing waves? It says standing longitudinal waves. I don't want that. Oh yeah, there you go. Okay, so this is showing you here is a wave that's not traveling. This is, and that's combining with that, and you get a traveling wave to the right. Okay. So two sine waves traveling in opposite direction. Yeah. So here is okay, we're going to send one wave to the right and an identical wave to the left. And this happens in musical instruments. When you pluck a guitar string, a wave will travel on the string to the right, and that will get reflected and travel to the left. And so these two waves are simultaneously traveling in the same medium and they combine. And here is the net effect. And you can see why it's called a standing wave. Does this look like it's traveling? No.
Can you scroll down a little bit? Can't see it. It's on the bottom.
Okay. So that's a standing wave. And in all musical instruments, that's what you're doing. You're exciting standing waves. Okay. And then, of course, you have to figure out a way to amplify it. Okay. Just the string vibrating, you couldn't hear that sound. Okay, so in an acoustic guitar, that vibrating string amp the sound box is that air in the acoustic thing. In an electric guitar, you use you amplify the electric current. Okay, and we'll talk about that next semester. Okay. All right. So in musical instrument, okay, so every object has a natural frequency of oscillation. Okay. So here's a string of this length. The frequencies it likes to oscillate at is the following. Nodes at the end. Okay, so the endpoints are not oscillating, and so this is the lowest frequency, this is twice that frequency, this is 3 times that frequency. So these are the harmonics. Okay. So if this is 100 hertz, 200 hertz, 300 hertz, okay, that's the frequencies it likes to oscillate. Okay, so the frequency, natural frequencies of oscillation are N is an integer, L is the length of the string, T is the tension in the string, and mu is the mass per unit length. Okay, so here's a string that can only vibrate in certain frequencies. So how do you produce music when you're playing the guitar?
By playing different strings that vibrate at different frequencies.
Okay, so that's only 6 frequencies. Okay, that's before you started playing.
Pressing on the fretboard to change the
Length. So there's your, so that's all the control you have. You can change the length of each string, and then you can choose 6 strings to play from. Okay, and that's enough choices. And I'm going, this application I'm going to show you because it's beautiful. Here's a drum head. Okay, so a string, the higher frequencies are integer multiples. So this is, these are higher frequencies are integer multiples. They're harmonics. On a drum head, this is the lowest frequencies. You see the next frequency is 1.59. It's not an integer multiple. So these don't form harmonics. Okay. And no, not forced oscillation. Oh, yeah. So there you go. So that's the lowest frequency of oscillation on the drum head. Okay, so you hit the center, and that's what you would excite. Okay. So when you learn to play the drum, you're learning to hit at various spots. Okay. It's beautiful. Okay. Here is an amazing thing that, so I want you guys, I want you to go there and read that Wikipedia page. The question is the following. This was a famous problem. So it seems like the thought was the following. Different shapes would produce different frequencies. Okay? Given everything else being the same, made of the same material and stuff like that. Okay, so let's say. So the question is the following. So here's this drum shape and that drum shape. And the question is, by just listening to the music produced from that drum, can you tell the shape of the drum? And that was the question, and it was a mathematical question. And it turns out that if the area and the perimeter are the same, then it'll produce the same frequencies. So, but other than that, you could tell the shape of the drum. Okay, so. All right, guys, I will see some of you guys in lab. Okay.